oxidation numbers. So today we're going to how to assign oxidation numbers to particular entities, atoms, electrons, molecules, etc. And then in the next couple of days, we're going to start to balance them in acidic reactions or neutral solutions. So in some cases, this case in particular, it's fairly easy to see that we're going to have a change. We go from a 1 plus to a 0 because we have a silver ion. It has one extra or one less electron than proton, and it goes to an elemental form where it has even numbers of protons and electrons. The copper goes from elemental form, no imbalance in protons and electrons, to a 2 plus. So it's fairly easy to see that the silver ion gains an electron and the copper loses 2 electrons because we have this understanding of metals and metal ions. It's also fairly easy to see since the NO3 stayed the same. It didn't change. It's our spectator ion in this case. So generally we have this, let's use the word generalization twice. We have this generalization. Metals and anions, so negatively charged ions, will lose electrons, as the copper did in this case. Nonmetals and cations will gain electrons and be reduced, as the metal silver ion did in this case. What about this? Well, for the first one, we have a 3 plus and we go to a 0. So we can see that we have a gain in this case. But what lost? Because carbon is not an atom, not a metal. It doesn't have a charge. It doesn't have a common ion charge. And as far as I know, it doesn't have any ion charge. Same thing with this. What gains and what loses? Well, we can kind of see that one of these oxygens over here, is going to lose electrons to become that oxygen there, but what else changed? Okay. So it's very hard for us to take a look at that and go, In this case, this one here, it's much easier to look at that and go, okay, yeah, that makes sense to me. But this one, I don't know. So what other scientists came up with to make life easier is what is called the idea of oxidation numbers. It is not what is actually happening because carbon doesn't get a charge, and lots of other things don't either, but it is useful for our process. Which one of these gains electrons in terms of hogging them or losing, or gets them more often, gets them less often? So the oxidation, it's a bookkeeping. It is a method. It doesn't reflect reality all that well, but it does help us with this system. An oxidation state of an atom is of an entity, or of an atom in an entity or molecule, or when I say entity, I mean molecule or ion, is defined as the apparent net electric charge the atom would have if the pairs in the covalent bonds belong completely to the more electronegative ion. This is where it becomes difficult because we haven't really talked too much about this last year. Let's say I have something like carbon monoxide, okay? When we look at our electronegativity on our data book, we find that this is 3.4 and this is 2.5. And these numbers tell us that the higher the number, the more the atom will attract electrons due to the number of protons in it, the electron shell, etc. So right now with this carbon monoxide, the oxygen is going to try to steal electrons off of the carbon. And so that guy here would mean he's got 2 extra electrons. He hasn't ripped them off, but he has pulled them away from the carbon a little bit. So based upon this electronegativity idea, we can assign some numbers. Now I'm going to give you some basic numbers on this. Again, if I have something like, well, let's not do that one. So in this situation, again, we have our 4 bonds. What we can see is each of the chlorine, because it wants to fill 1 electron, so there's 1 bond. Each of the chlorine is stronger than the carbon, so the carbon is going to lose electrons, or maybe not lose. We'll have them pulled away from them more often. The electrons will hang around the chlorine more often. And that means, based upon this idea, we're going to assign the chlorine a -1. And we'll talk about that in a minute. We don't really worry too much about chlorine, but chlorine will have an apparent charge of -1, i.e. an oxidation number of -1, and the carbon is going to have an oxidation number of +4 because he loses, or doesn't get to share these electrons equally with the chlorine, 4 of these. Okay, that's based upon electronegativity. Again, I'm going to give you some simpler rules to help you. With this one, as I said, it's useful. It allows predictions, good predictions, but again, it's not actually what happens. Going back to this, the chlorine doesn't actually rip the electron off the carbon. He only shares it unequally with them. I'm going to keep this for 70% of the time. You get it for 30% of the time. So here are the simple rules. Only 5 of them. So if you have an element an element in its elemental state, you assign that one a 0 oxidation. That means there's no imbalance in electrons and protons, real or apparent. So if sodium is by itself, you assign it 0. If Cl is in the form Cl2, which is its elemental form, you assign it a 0, or a 0. Okay. So anything in its elemental form gets assigned a 0 because there's no apparent or real electron charge. Hydrogen, for our nonmetals, has a very, very low attractiveness for electrons. That means in just about every element it's ever going to be with nonmetals, it is going to lose an electron, apparently. It's going to share it unequally, and it's not going to get the strongest part. So you assign the hydrogen a +1. Anything hydrogen is in its molecule, in a molecule gets assigned a +1. Oxygen is the second strongest. Has the second strongest attractiveness for electrons. It's going to pull electrons off everything but fluorine. Okay, so with two exceptions that we'll talk about, we assign oxygen a -2. The exceptions don't come in very often, but we do want to talk about them. So the O in the H2O is assigned a -2. Fluorine, being the most reactive nonmetal, it has the strongest attractiveness for electrons. It's always going to be a -1 because it has the strongest attractiveness for electrons. Now, monatomic ions, Na plus, Ce2 plus, etc., we will assign them because it's not an apparent net charge, it is actually a charge of +2 or -1, depending upon what it is. So we assign whatever the charge on the ion is. So when we have something like CH4, the overall charge imbalance in this guy is there's an even number of protons and an even number of electrons. We know hydrogen has a +1. I have no idea what carbon is. So I'm going to assign it NX. Because this is going to help me figure this out. And I'm going to create a mathematical equation. Yes, I'm a math geek, I know this. We have one unknown. We have 4 hydrogens, each with a +1. So that's 4. I have 4 of them, each losing an electron to something. And that overall charge has to be equal to 0. Because that's the overall charge here. We have an equal number of protons and electrons. And we get to solve that. Carbon must be assigned an oxidation state of -4. And what that tells me is that carbon has a stronger pull for electrons than the hydrogen. So it's going to get the electrons just a little bit more often than the hydrogen. And we're going to do that 4 times. So that's why we get a -4. He has 4 apparent extra electrons. Now, I am missing a typo here somewhere. MnO4 negative. Okay, put a negative sign up there. So what that means is there's 1 extra electron in this system. So when I make my equation, I have to equal it to -1. Because we do have 1 extra electron in the system. Each of those oxygens will have a -2 charge, and this manganese will have an unknown charge. We don't know what it is. So again, I have 1 unknown. I'm going to add that to 4 oxygens, each with a -2 charge. X minus 8 is equal to -1. X is equal to +7. So that means that manganese looks like it has lost 7 electrons to the oxygen. Again, this is an apparent, not what actually happens, but it's what we're going to say happens for this number. So the manganese in this situation is +7. If I have manganese 3 plus, that guy's going to be assigned a +3 charge. It is dependent upon what entity it's in. So we're talking about entities are considered to be elements or ions. So that's what I mean by the word entity. We can do the same thing down here. Okay. We want to know the oxidation numbers for these species. Well, according to my rules, we know the oxidation number for a lot of those elements. Each oxygen, because it's in each of these oxygens, because they're in molecules, are going to be assigned a -2. This oxygen here can be assigned a 0 because it's in elemental form. Each hydrogen will be a sign of +1. So this, we've already done water. Hydrogen has +1, oxygen has -2. We have to figure out the carbon in here. And we would have to figure out the carbon over here, but we already did that above, so it's not a big issue. So I would like you to find out what oxidation state or oxidation number you would assign to the carbon in the carbon dioxide. So we have our unknown. We have one of them. Now, if it was C2O2, you would have to put 2 Y's. Just make sure you always have that. For some reason, I haven't given examples of this. Plus, I have 2 oxygens, each with a -2, and that reaction has to add up to 0 because the charge on the CO2 is 0. It's a molecular compound. The overall charge is always going to be 0 on compound. So in this case, the carbon has a +4. You notice that the carbon has changed from -4 to +4. What would that mean in terms of electrons? Does it gain or lose when it goes from -4 to +4? It has 4 extra apparent electrons here. It has 4 less electrons over there. We have a loss of 8 electrons each. And I'll point out why I use each later. Okay. Here we have the oxygen going to both of those. It goes from a 0 to a +2, or sorry, to a not -2. This is a gain of 2 electrons each. Considering I've got 4 oxygens here, I end up gaining 8 total. Okay, we'll talk more about this gain and loss in a minute. Okay, so we talk about this. It's arbitrary because it's based on assigned charges, but it is self-consistent and allows predictions. Okay, so that's why we get to use it. It's self-consistent. It's consistent throughout all of the stuff that we use. The oxidations, if you change the oxidation state during a reaction, we've got an electron transfer, i.e. a redox reaction. I'm going to copy this down. An increase i.e. going from a negative to a positive, or from a positive 1 to a positive 3, means that the species, the atom has lost electrons and is therefore oxidized. A decrease from +7 to +2 means a species has gained electrons and is reduced. So going back here, we can see that we went from -4 to +4. He lost. And the more negative a number means the more apparent electrons it has. So -4, he's got 4 extra electrons hanging around itself. Over here, the oxygen stole all those. Now he has 4 not hanging around. He's lost 4. A slightly more visual version of what we just saw. So in this case, because the carbon lost 8 electrons, the carbon is oxidized in this case. Therefore, the methane, where the carbon is the reducing agent. The oxygen is reduced, is the oxidizing agent. One thing I want to point out while you're writing, notice balanced equation. Each carbon lost 8 electrons. Each oxygen gained 2. I have 4 oxygens over there. I have a grand total of 8 electrons being gained. Therefore, what we have here is everything is balanced. Everything follows the law of conservation of matter. The electrons lost, somebody had to gain them. I'm going to do the CR207 with you, and then I'm going to ask you to do the remaining. So my first step, if I was to do, first step in this would be balance the equation. Well, how are we going to balance it? We'll talk about that later. To find the oxidation and reducing agents, I need to find out which one gains electrons, which one loses electrons. Let's assign oxidation states to what we know. The hydrogen is +1. I don't know what that carbon is. I'm going to assign it a Z. I'll show you why in a minute. That high. And then that carbon is also a Z. This oxygen is a -2. That guy's a +1. What's the chromium? What's the chromium 3 ion? What's its oxidation state? It's a monatomic ion. Its oxidation state is +3. It is the same as the ion. Okay, we have to go back to our rules that we started earlier. That's not in the data or in the data booklet. You have to remember that rules from the chart. We have, just go back and do all the oxygens and hydrogens. I'm going to call this carbon Y because we don't want to have the same thing. That guy's a +1 because of its charge. This guy's a -2. And this guy we're going to call X. Okay. So yes, this equation is balanced. This 2 does not exist in terms of what we're doing. We're only looking at the complex, or the ion Cr2O7 2-. So don't worry about the balancing part. We only want to look at what the entity is. We have 2 unknowns, 2 Crs. We have 7 oxygens, each assigned a -2. And I have 2 extra electrons, so I have to make that. I want to have all of this side equal to those 2 extra electrons. 2x minus 14 is equal to -2. 2x is equal to +12. X is equal to +6. So this chromium is a +6. Each of those chromiums has an oxidation state or oxidation number of +6. Please find what the oxidation states of the carbon are in the ethanol and the carbon is in the acetic acid. I'll give you a couple minutes to work on that. Let's see. One oxygen. One oxygen. How long? They're very compound. Just walking around, it looked like everybody had an idea. So the equation that I'm going to create here is I have two unknowns. I have 6 hydrogens with +1. I have 1 oxygen with -2. This is a compound, so it's going to add up to, sorry, it's going to equal to 0. Remember, that means that there are no extra electrons or protons. Okay, so gather everything together, we get y is equal to -2. Over here, we have 2 unknowns. We occasionally forget that one because it's written in a structural formula. We have 2 unknowns. We have 2 oxygens at -2, 4 hydrogens at +1. Okay, so we have Z is equal to 0 and Y is equal to -2. So what? We have 2 things. We have our chromium. It's going to get a little messy because I'm going to draw here. We have our chromium going from +6 to +3. What did it do? Did that gain or lose electrons? Going from +6 to +3, that's a gain of electrons. In this case, gain of 3 electrons each for a grand total of 6 electrons. We have the carbon here going to there. It went from -2 to 0. What is that? I gotta change this. That is a loss of 2 electrons each. Now in this case, because I have 6 here, I lose 12 electrons total. Now the 2 in front of this, the 2 and the 3 come into account. I have 4 chromiums here. I end up with 12 electrons being gained also. That's what we're going to do there when we start to balance these. That's what we're going to work with. So the chromium or the chromium in the dichromate gained electrons. What is he? The oxidizing agent or the reducing agent? Did he cause the other guy to gain electrons, or did he cause the other guy to lose electrons? Since he gained electrons, the other guy lost. So the dichromate is the oxidizing agent. The loss of electrons means that the ethanol, the compound ethanol, is the reducing agent. Forget you. Maybe don't. So I'm going to talk a couple other issues that we have when we do something like this, assigning oxidation states to something like this. I want to assign oxidation states to all the entities in NaHCO3. Okay? The first thing you have to recognize is that's an ionic compound. So I can treat this as Na plus and HCO3 negatives. Okay, it's an ionic compound, so it's made up of ions. So now we have a monatomic ion, so the Na will be a plus 1, treated separately. And now you can do our equation here. HCO3, we have plus 1 minus 2, 1 unknown, plus 1 hydrogen, plus 3 oxygen, equals to negative 1. That's supposed to be a plus sign. We have the carbon in that case equaling a positive 4. So when you have an ionic compound, treat it as the 2 separate ions. And then we have our 2 exceptions. Or the 2 exceptions that show up that I'm going to talk about, because there may be more. The first one is something where oxygen is combined with fluorine. Okay. By experimental study, we know fluorine is more attractive for electrons than oxygen is. We can see this by the positive or the 4 oxidation. Oh, sorry. The 4 assigned for its electronegativity, and oxygen only has a 3.4 assigned for its electronegativity. So in this case, the fluorine would have a negative 1, and we would have to have a positive 2 for the oxygen, because we have to add up to 0. So when oxygen would be combined with fluorine, you would have an exception to that negative 2. The other one that shows up very often is the H2O2. Okay? Now, in this case, we have to talk about the structure a little bit. So this is what we have here is each oxygen onto 1 hydrogen here. So in this case, this hydrogen is going to lose 1. So we're going to assign the oxygen a plus 1. So if we assign a negative 2 to these oxygens here, we're going to assign the hydrogen plus 1. If we assign an oxygen negative 2, it's not going to end up to 0. What we have with the structure of H2O2 is the oxygen is pulling 1 off the hydrogen, but then it's trying to pull 1 off this other oxygen, and it doesn't happen. So in this case here, it's an exception. The oxygen would have a -1 charge because you have each oxygen getting an electron from the hydrogen, but not from each other. So those are the 2 exceptions that show up regularly. We will discuss any questions you have during chemistry.